The next talk is on rate 1 arithmetic garbling from homomorphic secret sharing by Pierre Meyer, Claudio Orlandi, Lawrence Roy, and Peter Scholl. And Lawrence is giving the talk.
Hello, everyone. In my talk, I'm going to discuss techniques for homomorphic secret sharing, their application to arithmetic garbling. This is joint work with Pierre Meyer, Claudio Orlandi, and Peter Scholl. So in Boolean garbling, a party called the garbler takes a description of some Boolean circuit C and turns it into a garbled circuit tilde-C, together with wire labels representing the bits 0 and 1 for each input to the circuit. Once inputs are chosen, the evaluator can then take the garbled circuit and the wire labels corresponding to these inputs and compute the output of the garbled circuit. For security, the evaluator must not be able to guess the wire label corresponding to a wrong value in the circuit. Now this has been generalized to arithmetic garbling, where the circuit is now an arithmetic circuit over some ring, and the inputs and outputs are taken over that ring. So now the two possible input wire labels become one possibility for each value in the ring, and they're encoded into labels using a secret linear function. Now some schemes, Boolean schemes satisfy free XOR, where the difference between the two wire labels is the same secret key for every wire. Similarly, some arithmetic garbling schemes use the same linear multiplier sk to encode all the wire labels. So the point of setting these to be equal is that this makes them into like a homomorphic MAC. If you add two labels together, then you end up with a valid wire label for the sum of the two inputs. So in this work, we focus on arithmetic garbling for bounded integer computations. This means that the ring we are working over is the integers, but as these are infinite, we have to consider only a bounded subset of L-bit integers. We are interested in the question of minimizing communication complexity. That is the total size of the garbled circuit and the input wire labels. Define the rate of the garbled circuit to be the size of all values computed in the plain circuit divided by the size of the garbled circuit. The higher the rate, the better the communication complexity. And in particular, we're interested in the asymptotic case, where the circuit size grows to infinity, as does the size of the integers. There have been a number of works building arithmetic garbling from various assumptions. First, there are several works based on symmetric key garbling, starting with the trivial case of using Yao's Boolean garbling to garble a multiplication circuit. Heath's result showed how to improve the rate to be 1 over the security parameter, which matches the Boolean case, or a big O of that, I mean. Next, we have schemes based on some kind of homomorphic encryption, which use homomorphic properties to implement arithmetic operations. So AIK11 showed how to do this based on LWE, beating Yao's construction, but the rate still depends on the dimension of the lattice. BLL23 then had this really cool result showing how to get constant rate garbling from DCR. In this work, we show how to use techniques from homomorphic secret sharing, in particular distributed discrete logarithms, to improve this to rate 1 and to support free addition. Specifically, our first scheme assumes that a variant of DCR under which Domgard-Uric encryption is secure for key-dependent messages, and gives rate 1 garbling of bounded integer arithmetic circuits. So that means the size of the garbling is similar to the size of all the values computed in the plaintext circuit added together. Our second scheme uses key switching to remove this KDM assumption, but only achieves a rate 1/2. So in my talk, I will focus on this rate 1 version, as it is much simpler to describe. So to start off, we have an observation on the form of these like free addition arithmetic garbling wire labels. So we have the wire label known to the evaluator and some offset ki known to the garbler that's used to hide the secret key and the value. And you can view these as being subtractive secret shares of the value, the secret key times the value the wire label represents. So yeah, the difference between the two shares is the secret key times the input. So this naturally brings up whether we can use techniques from homomorphic secret sharing to operate on these authenticated shares. In particular, we want to be able to implement both addition and multiplication operations on these authenticated shares. Now to give some intuition, let's look at roughly what like a distributed discrete log goal is. So if I have some subtracted, if I had some two group elements whose ratio is some g to the x, in other words, it's g to the x1 and g to the x0, such that the g to the x1 and x0, and then x is x1 minus x0. Then, well, if somebody knew g to the x, and x was in some like either small or there was some small subgroup such that you could compute the discrete log efficiently, you could just run the discrete log operation. For when it's split between two parties, there's this operation called distributed discrete log that gives shares of x from shares of the group element. Now, if you imagine a simplified version of the scheme, just to illustrate how you can put these pieces together for correctness, where we aren't going for security yet. We're treating exponentiation as if it were encryption. We can start out with some. This is sort of the key equation we use, which relates the product to different combinations of input shares and the values. So you can combine different shares together to show that why this equation holds. So then the idea is just that we have the first term is compute known just to the evaluator. The last term is known just to the garbler. And the middle two terms are the product of a value in the circuit with a value that's known to the garbler. And all these shares known to the garbler are fixed in advance, so the garbler can send encryptions to them. So if you imagine G to a particular value as being encryption, then we can just exponentiate them to shares of the value and take a distributed discrete log to get the cross terms. So then garbling the circuit would look like this. You start out with garbler shares of all the inputs, can compute a garbler share for addition. Then for multiplication, you need to encrypt the garbler shares. Then the garbler can continue doing this process, encrypt all the garbler shares, and you get garbler shares the output. And then once the garbler sends all these encryptions together with the validator's input shares, they can validate the corresponding inputs. Now there's one crucial trick we use, which is that rather than needing encryptions of both inputs, you could instead associate those encryptions with the gates they came from. The point being that you can reuse encrypted values, so I don't need to have two encryptions for every gate to encrypt the two inputs. I instead only need one encryption for every gate to encrypt its output, the other one encryption per input. So, yes. All right, so now to add in security, we use the distributed discrete log scheme based on Damgard-Urich. So here there's a easy discrete log subgroup where we can compute the distributed discrete logs over, and we have a way of encrypting values, and the secret key is going to be the order of the it's going to be Euler phi of n. So So the properties of this distributed discrete log mean that if I say some ciphertext C that's an encryption of some value y, then I can take C to the power of shares of the secret key times some value x, and take the discrete log to get secret shares of the product of the secret key x and y altogether. So this is how the homomorphic secret sharing scheme from Dahlgard-Jurek works, is that you can do this multiplication operation between shares and ciphertexts. And finally, if you want, at the end, you want to remove the secret key, you get just direct shares. Under this key-dependent message assumption, we can encrypt the inverse of the secret key and remove it, to use multiply to remove it. Now, putting this together, to start off, we would need to do these. If we want to compute shares of x times y, we can break that down term by term again, and the two cross terms will be multiplications of encryption of a garbler wire label and a share times a secret key, again, a share of one of the inputs. But the thing is, it's an authenticated share. It's a share times the secret key. So if we need that of the inputs, we also need to generate that for the outputs. So doing a similar equation here, associating the secret key with the y variable in the formula. Then you can still distribute this distributed discrete log operation on the cross terms to get secret shares of the secret t times x times y, which is what we need for the output. However, this requires some somewhat funkier looking terms, including both secret sharing of 0y level and the secret key times the 0y level encryptions of. So it would seem like we have 4 ciphertexts. Since Dahlgard-Jurek is rate 1, shouldn't that mean rate 1/4? Turns out the rate of this scheme is rate 1/3 because of the reusable encryptions again. The first 2 encryptions are the same form, so you can generate one encryption of that form for output every gate and reuse it across every case it's used. However, this scheme is not as symmetric as it could be, and we can do better in terms of reuse by generating something that outputs secret key squared. And then we just need encryptions of both 0 shares times the secret key. And then finally get secret key squared. You can remove the secret key squared down back to secret key by using the encryption of the inverse of the secret key. So this last step is where we do the key demand messages. And this is rate 1 again because we can reuse the 2 ciphertexts. Thanks.
I have one question. Do we have any evidence that we require public key assumptions for rate 1 arithmetic garbling or even Boolean garbling? Because without the rate 1 property, we can do it from one-way functions.
In terms of in terms of Boolean garbling, there are some models for proving lower bounds on symmetric key garbling. Currently, they're quite limited, but they seem to show that it's hard to do better than what you can currently do with lambda communication. I think there's a few going around right now that attempt to show that.
Okay, thanks.
So one question about your notion of rate. So I assume that you mean that there is a single ciphertext per gate. That's what you mean, because if you count the number of bits, it seems to me that once you move from bounded integers to this and embed them to this cryptographic group, then you already have some at least constant blow up in the size of elements.
Yes. So it's an asymptotic thing in terms of as the numbers get bigger and bigger. So Dahlgard-Jurek encryption lets you encrypt arbitrarily big integers with only additive blow up. And so that's why our rate only, of course, matters to the number of encryptions.
So you think of the size of the circuit as going faster than the size of the bounded integers? That's the point? The size of the integers is fixed? I mean, I can see how it goes how it can be
So if the size of the integers is sufficiently bigger than the security parameter,
sure,
then our rate approaches rate 1, because Dumb-guard your encryption. Essentially, the size is just the size of the integer encrypting plus the size of the RSA modulus.
Okay.
Okay, let's thank Lawrence again.